So in this video, we're going to develop the formula for the difference quotient, which is going to turn out to be just a different way of finding the slope of a secant line. So in the previous video, we reviewed what a secant line was. A secant line was just a line that intersected a graph in 2 points. And then we reminded ourselves that to calculate the slope of a line, one way to do it is just to do the slope of a line represented by m is equal to y sub 2 minus y sub 1, the difference in the function outputs, divided by x sub 2 minus x sub 1, the difference between the function inputs. And this is great. This is a nice, easy way to calculate the slope of a line. The problem is, in calculus, we are going to be interested in finding slopes of what are called tangent lines. So a tangent line to a graph is just a line that just touches the graph at a single point. So I would say this line right here is tangent to the graph of f of x at this point. And in calculus, we need to find the slopes of tangent lines. And it turns out that this formulation of the slope of a line doesn't lend itself towards easily finding slopes of tangent lines. So what we want to do is come up with a different way called the difference quotient for calculating the slope of a secant line, because it will turn out in later videos that it also gives us a tool for finding the slopes of tangent lines. So what we need to do is reconceptualize our slope of the line formula. So what we need is to, one, we want to make sure that if we're finding the slope of the secant line between 2 points, we want the function to be continuous over the closed interval between those 2 points. We should be able to draw the function without having to lift it from paper. There should be no discontinuities, no holes in the graph, no vertical asymptotes between x sub 1 and x sub 2, no jump discontinuities. In other words, the graph shouldn't be moving along like this. If this is x sub 1 and here's x sub 2 sitting over here, I shouldn't have a jump in the graph. So as long as the graph is continuous between x sub 1 and x sub 2, then we can talk about finding the slope of the line connecting those 2 points. So here's the idea. The idea is we know that x sub 1 is just a number on the x-axis, and x sub 2 down here is just some number on the x-axis. In the same way that y sub 2 is just a function output sitting on the y-axis, and y sub 1 is just a function output represented on the vertical y-axis. And what we want to do is represent the distance between these two numbers. X sub 2 minus x sub 1 just gives us the distance between the two numbers on the real number line. We want to represent that as delta x, or change in x. It's also pretty customary to do y sub 2 minus y sub 1, the distance between those points, as delta y. So sometimes you'll see the slope of a line represented like this. M equals the change in y, which is just the distance or difference between those y coordinates, divided by the change in x, or the distance or difference between those x coordinates. So we let delta x represent x sub 1 minus x sub 2. In other words, let delta x represent the distance x sub 1 minus x sub 2 minus x sub 1. And if we do that, then we can replace the x sub 2 minus x sub 1 over here with just the symbol delta x. We're letting delta x be this difference. So that's step 1. Step 2 is to recognize that the function output y sub 1, the function output when at x sub 1, is just the same thing as taking the function and plugging x sub 1 into it. Similarly, y sub 2, the function output when the input is x sub 2, y sub 2 is just the function evaluated at the input x sub 2. So y sub 2 and f of x sub 2 are the same thing, and y sub 1 and f of x sub 1 are the same thing. So y sub 2 can be replaced with the function evaluated at the input x sub 2, minus y sub 1 can be represented also by the function evaluated at the input x sub 1. So this is another way of saying y sub 2 minus y sub 1 divided by delta x means x sub 2 minus x sub 1. So there's step 2. So the next thing we want to recognize is that one of the things that it's customary to do is to give delta x a name. So it's common to call delta x h. So let delta x be represented by the letter h, which means I can replace delta x with h, and that means that h is just the distance between those two numbers. H is just the distance between them. So x sub 2, if I want to know what x sub 2 is, all I would need to do is take x sub 1 and add the distance h to it. X sub 1 plus the distance between the two numbers will give me x sub 2. So if I do that, I could actually replace x sub 2 with x sub 1 plus the distance between the two numbers, h, minus f of x sub 1. So this is still y sub 2 minus y sub 1 over h is delta x is x sub 2 minus x sub 1. So this is still the slope of the secant line, just written in a different format. So finally, the last step, what it's customary to do, because x sub 1 is just some arbitrary x, is just say, hey, let's just call it x and drop the subscripting, which means to get to x sub 2, we just take whatever x we want that comes before x sub 2, and we add h to it, the distance between x sub 1 and x sub 2. So if we drop the subscripting from x sub 1, we just get f of x plus h minus f of x all over h. And this is called the difference quotient. And the key is to recognize that the difference quotient is just a different way of calculating the slope of a secant line through a series of symbolic manipulation. This is the slope of the secant line. This is the slope of the secant line. But it turns out that this way of representing the slope of a secant line is going to be conducive to finding slopes of tangent lines. So then the summary slide, I'll wipe all that out. The summary slide here is just to put all of that work into a nice little brown box here. Suppose that we have a function that's continuous between two numbers, x sub 1 and x sub 2 over the x-axis, which we represent by x and x plus h, where h is the distance between x sub 2 and x sub 1. Then the slope of the secant line, m sub secant, the slope of the secant line is given by the difference quotient. And it's going to turn out to be the case that this is can also be called an average rate of change, which we will explore in subsequent videos.